Good morning. Happy Monday. Welcome to May. Today I was going to go over the notes, new chapter on work, power, and energy. And today's notes are just about work. In classroom, you guys will have an assignment, fill out the notes, and answer some questions that go with it. So I was just going to do the PowerPoint in this video, and then you can use this to help fill in all of the notes. So here we go. All right, basically what work is, it's the transfer of energy to an object which must be moving parallel to the force being applied to it. All right, so what that means, if you have any form of energy and you apply it to an object, you're doing work. The key thing is the work and energy have to be moving parallel to each other. So if you're pushing a box across the ground, you're doing work. If you're picking a baseball straight up, you're doing work. If you're pushing on a wall, but the wall is not moving, then you are not doing any work. The object has to be moving. We measure work in a unit called joules, gets a capital J. And in order to do work, you have to use energy. Right? And we're going to learn about energy later on, but work and energy go hand in hand. You can't do work without energy, and without any energy, you can't do work. All right, think about yourself. If you want to do anything, you need energy. Our energy is food, but if you don't eat, you can't do anything. All right, we talk about work, we always say it's done on something by something else. So if you push a shopping cart, work is done on the cart by you. Right? I'm trying to think of another good example, if you push somebody, they're getting work done to them by you. Okay, so that's what we always think of it in terms of that. So state what the work is on and who is doing it. So for the first one, a ball drops to the ground. So who is doing the work? Well, what causes everything to drop? Gravity. And who is gravity doing the work to? The ball. So state what the work is on and by what. The work is done on the ball by gravity. All right, you push a lawnmower across the floor, hopefully across the grass, not just the floor. That would be weird. So who's doing the work? You are. What's having the work done to it? The lawnmower. So the work is done on the lawnmower by you. Okay. An electron is released from rest and accelerates towards a positive source charge. So who's moving? Who's having the work done to it? The electron. What's causing it? The positive source charge. So the work is on the electron and it's done by the positive source charge. All right, and last but not least, the Earth revolves around the sun. So the work is on the Earth, and what's doing it? Well, it's not really the sun here. It would be gravity, or the sun's gravity. So work is done on the Earth by the sun's gravitational force. All right, so here's another one. Is gravity doing work on a ball that is just sitting on a flat desk? Well, we know there's a force, gravity is applying some force to it, but the ball isn't moving. In order for you to do work, you have to be moving. So the answer is no. Is gravity, okay, good. Sorry, I thought I was stopped recording it for some reason. I apologize. Let's go back to this. Sorry about the break, guys. Okay, sorry about that. Okay, so again, gravity does not do work here because the ball isn't moving. Let's look at the next one. Is gravity doing work on a ball that is rolling across a flat desk? Well, now the ball is moving, so we hit that category, so that's good. But the other part is the work, whatever applying the work needs to be doing it in a direction that's parallel to the object. Well, we know gravity only works up and down in the y, and if the desk is flat, it's moving in the x-axis. That is not parallel. In fact, that's perpendicular. So in this case, gravity is not doing work on the ball. Okay, right? The gravity is not causing the ball to roll across a desk that is flat. So that's why the second one would be no. Do you do work on a book as you lift it from your desk to over your head? Well, you're doing work, right? You're picking something up so it's moving, that's good. And you are applying a force to it and it's moving in the same direction that you're applying a force. You're picking it up, the book is moving up. So yes, you are doing work there. But if you keep it above your head and you're just holding it above your head, are you still doing work? And the answer is no, because even though you're holding it up there, since it's not moving, you need to be moving the object for it to be doing work. So the last one would be no. Right. So to calculate the formula for work, it's work equals force times distance. All right. Units for work are joules. And because there's a force involved, forces are vectors, so work is also a vector because you can have a direction with work. So that's why it's a vector quantity. Okay. So you gently lift a 2-kilogram bag of groceries a distance of 0.8 meters at a constant velocity from the floor to a table. How much work did you do lifting the force to the bag? Okay, so let's think of it like this. All right, so let's write in our givens. So we know D is 0.8 meters. The other thing we need to define force, or I'm sorry, define work is force, right? But we don't know force, but there's a hint here. The force required to lift the bag is at a constant velocity is equal to the weight of the object. Well, we know to find weight, that's the force of gravity. So force is m times g, 2 times 9.8, and that's 19.6 if you multiply those two together. Okay. So we found the force, we found the distance. So to find work, work equals F times D. And I'll save you guys the sloppy handwriting. I'll just solve it on a calculator I have real quick. So we multiply 0.8 times 19.6 or other way around. Either way, it doesn't matter. You get 15.68. joules. All right, so there you go. All right, let's try the next one. So now we're talking about work and direction. When an object moves in the same direction as the force is doing positive work, and it's giving energy to the object. If you're moving in the opposite direction that the force is acting in, the force is doing negative work on the object and it's taking energy from the object. Right, so if you are applying a force and you're doing work and all works in the same direction, you're positive and you're applying energy or you're giving it energy. And then if the object is moving in the opposite direction of the force, then that force is doing negative work on the object and it's taking energy away from it. Right? And when the movement is perpendicular to the force, no work is done. We said that before. So let's think about these. A pitcher throws a fastball. Does this force do positive or negative work on the ball? Well, when the pitcher throws the fastball, the direction that the pitcher applies the force is the same direction that the fastball is moving. So the pitcher is giving the ball energy. So in this case, the force should be positive. The ball comes to rest in the catcher's glove. Does the glove do positive or negative work on the ball? Well, the ball is moving, let's just say to the right. And then the catcher's mitt stops the ball moving to the right. So it has to take energy away from that ball to bring it to a stop. So that work is negative. All right, so the first one is positive, the second one is negative. Think about your car, okay? When you hit the gas pedal, you are providing energy to cause the car to move forward, and that's the direction you're wanting to move in. So that is a positive work. When you apply the brakes, you're taking energy out of the car, all right? And that's what's slowing it down. So that is negative work. All right, so get this clip here of this lady who ran in front of a man on the track. Just pause it right while she's getting demolished. Whoop. So who is doing the work? Well, the guy with the yellow hair is doing the work. Who has the work done to them? That would be the woman who is getting blindsided by the guy. So is the work positive? What work was positive? So him moving is positive work, all right? He's pushing her in the positive direction. Is there any work that is negative? In this case, no. No. So just like forces and have net force, we can have net work, right? And net just means the sum of all of the works being done. So here's what we got. A box is initially at rest on a rough floor and is accelerated to the right by an applied force of 10 newtons over a distance of 5 meters. A constant force of friction of 4 newtons acts as it slides. Determine the work done by the applied force, by friction, by gravity, and the normal force, and then find the net work done. Okay. So lots of things here. Seems much more involved than it really is. So we're going to solve each one individually. So find the work done by the applied force. So we know work is force times distance. So work A for applied. Okay, so the applied force is 10 and the distance was 5. And that would be 50 joules. And that's to the right. Okay. And then friction is another force. So now we'll do work friction. Okay. Well, its force is 4, and it also worked for the 5 meters. And that's 20 joules. But this would be to the left. Okay. Determine the work done by gravity and the normal force. Well, we need to do a formula here because the object is not moving in the direction of gravity or the normal force. That's in the y-axis. This object's moving in the x-axis. Since it's not moving in the y-axis, there is no work done. So if we want to find out the net work, we're just going to look at these two things right here, 50 and 20. Since they're going in opposite directions, all right, we would do net work is 50 minus 20. So how much net work is being done? 30 joules of work. That's the net work that's being done. So we found the first work, we found the second work, and then since they're going in opposite directions, we subtracted them because it's a vector problem. All right. So let's do another one. 1 sec, I just gotta take a quick pause. Give me 1 sec, guys. I have to get my kids up with another episode of Sid the Science Kid to watch or Magic School Bus, not sure which one. 1 sec. Sorry about that. We set it on Magic School Bus. Okay, so let's continue. Okay, so we just did this net force problem, or sorry, network problem. So let's look at the next one. All right. So to train for football, an offensive lineman pushes a blocking sled, which is 50 kilograms, with a force of 1,000 newtons over a distance of 2 meters. The force of friction produced over these 2 meters is 750 newtons. Find the work done by the offensive lineman, find the work done by friction, find the net work done, and find the acceleration of the blocking sled. Okay, lots of stuff here. All right. Again, we're going to solve each one individually. So we'll start with find the work done by the offensive lineman. So again, work equals force times distance. So work, I'm just going to put a little OL down here for offensive lineman, is force times distance. So 1,000 times 2, and that obviously is 2,000 joules. Okay. Then find the work done by friction. So work friction, same thing, force times distance. Well, in this case, the work is, or I'm sorry, the force is 750. The distance is the same. So 750 times 2, and that's 15, oh my, 1,500 joules. Okay, so find the net work done. Well, let's think real quick. We know friction always works against your motion. So these things are going opposite directions. So it's going to be 2,000 minus 1,500. So the net work is 500 joules. Okay. All right. Find the acceleration of the blocking sled. Okay. So this one, we have to kind of think back now. So the formula for work is work equals force times distance. All right, well, we know the overall work, the net work being done is 500. Okay, we want to find out the net force. We don't know the net force, but actually we can do this instead. We know force equals M times A. So what's the mass of the sled? 50. Okay, A is what we don't know. We'll call, we'll leave A. And then we know that it was applied for 2 meters. All right, so if we do this, this is 500 equals 100, 50 times 2, times A. So if we solve for A, we divide 100 by both sides, and we get it accelerates at 5 meters per second squared. So what we do, we first found work by the offensive lineman, force times distance. We did the same thing for friction, force times distance. The net work, we subtracted since they're going in opposite directions. And then to find the acceleration, we use the net work, 500. Instead of solving for F, we just turned F into M times A. You could solve for F first and do it in 2 parts. We know force is always M times A, or the mass of the sled is 50. A is what we're trying to find. And then distance is still 2. So then we solve for 5 meters per second squared. All right, so let's try. All right, got a couple more sets of notes left and then we're done. All right, so everything we've done so far is with no angles. Well, we can also do work with an angle. So when you apply a force and we're applying at an angle, we need to find out the components. Unlike before, we just need to find out the parallel component. That's always the x component. So we end up with this formula. It's work equals force times distance, and we just add cosine theta to the end. You have to be in degrees. Use the right calculator, Maddie Heron. Okay. Theta has to be the angle between the force and displacement vectors. Don't worry about that. You would never have an issue where that's not the case. And then what would theta be if the force and displacement are parallel and perpendicular? Okay. Well, we know that if theta is parallel, that means it's perfectly level to the ground. We call that angle 0, and the cosine of 0 is 1, so it just disappears. If it's perpendicular to the ground, we would say that's 90 degrees. If you plugged in 90 degrees into this formula, the cosine of 90 is 0, and then that means anything times 0 is 0, and that's why if the work is being done, you can't do work perpendicular to the direction of the force. It's impossible. That goes back to that problem in the beginning. We said, is gravity doing work on the ball as it rolls across the desk? And the answer is no. Why? The ball is moving in the x-axis and gravity is in the y-axis that's perpendicular. And according to this formula, if you were to plug all those numbers in, you would end up with 0. So let's try 7 out. So a box is slid 5 meters horizontally across a frictionless floor by an applied force of 10 newtons at 30 degrees. Find the work done on the box. So for this one, it's just plug and chug. So work, all right, so we are applying 10 newtons of force over 5 meters at an angle of 30 degrees. So cosine 30, and then we just solve. So 5 times 10 is 50, and then times cosine of 30, you get 43.3 joules. Okay. All right, one more practice, and then that is it for today. Okay, so this is like the one we did before. Now it's just with an angle. So a rolling luggage bag is pulled at 20 degrees with a force of 30 newtons across the ground. The luggage is pulled for 10 meters and the force of friction is 18 newtons. So let's find all of these things. So to find the work done on the luggage, all right, it's work equals force times distance. Oh. Okay, so work luggage, it's going to be force 30, distance 10, cosine theta, which in this case is 20. So if we really quickly solve for this, 30 times 10 is 300. Cosine 10, you get 281.9. Let's just make it 282 joules. All right, to find friction, it's force times distance. So the force is 18 and the distance is 10. There's no angle here because friction is parallel to the floor. So the friction is not being applied on an angle. So that's why there's no cosine part for this one. So 18 times 10 is 180. So the net work is going to be the same thing. It's going to be 282 minus 180 because we know they're acting in opposite directions. So 282 minus 180. All right, that gets us a net work of 102 joules. Okay. All right, and then last question. Is the luggage accelerating and in the direction, is the luggage accelerating in the direction it's being pulled in? How do you know? Okay. So we know that overall there is a net work being done, right? We know this, 102 equals force times distance. We know the distance is 10. We actually don't have to do any math here. I'll show you how we do without any math here. Well, since we know that F is going to be some number other than 0, we know there is a net force applied to an object. And we go back to Newton's laws, Newton's second law, okay? If you apply a force to an object, it's going to accelerate. So is it accelerating? Yes. And is it accelerating in the direction it's being pulled in? Well, yes, it is. And we know that because if we look back at our top 3 answers and we look at net work at the ends, we know that our overall answer is going in the same direction as the work of the luggage because 282 minus 180 is a positive value. We made 282 positive. So the luggage is accelerating and it's accelerating the direction that we are pulling it in. And we know that overall, because there is net work being done to it and it's positive, and that's the same direction that the luggage is being pulled in. All right. So that is the notes for today. Okay. So what I'd like you guys to do, fill out the notes as always, all right, and then just send them on in. Have a good day. Tomorrow we'll do some practice with it, and I'll get your grades posted also from your literacy quizzes test by today. Overall, you guys did ridiculous. I think the class average overall was over a 90. So 2 thumbs up. Also, this is the last unit. So we're gonna do work, power, energy, and then if we have time, momentum, and then done. All right. So stay safe, guys. Miss all of you. Talk to you later.